In this video, we're going to discuss R matrices. In R, matrices are effectively vectors with a dimension attribute attached to them. This dimension attribute specifies the number of rows and columns of the matrix, and R provides a number of operators and functions that operate specifically on these structures. Since matrices are essentially vectors, they can contain non-numeric types, but for this notebook, we're going to focus on only the numeric matrices. Also, R does support k-dimensional matrices, that is, matrices with more than the two dimensions, rows and columns, that you're probably accustomed to seeing. Again, this notebook is going to stick with just the 2D matrices. So to get started, let's create a vector containing some numeric data. And so there's nothing different here. We have a linear vector of integers 1 through 6. So if we now use the dim function and pass our vector a, we actually get null as an output. And this is because by default, there is no dimension attribute for a vector. But we can create one by simply assigning a value to the dimension attribute. The value we assign here tells the number of elements that we want in each dimension of the matrix. So for the standard 2D matrix with rows and columns, we will pass a vector of length 2, containing the number of rows and columns respectively. For a k-dimensional vector, we would pass a vector of length k here. But for our example, we have a vector A containing 6 elements, and let's say we want 2 rows and 3 columns. And if we now look at the output, we see that the data in the vector was applied in column order, meaning that each column of the matrix was filled from the vector before moving on to the next column. That is, the first column of 2 elements received the first 2 elements from the vector, namely 1 and 2. The second column received the next 2 elements, 3 and 4, and the last column received the last 2 elements of the vector, 5 and 6. Another thing to note here in the output is that Jupyter Notebook is doing a little bit of extra formatting for us. It recognizes the matrix type and outputs a message telling us that A is a matrix, and it has dimension 2, 3, and then it also tells us the type of data within the matrix, which is int in this case, and then it outputs the actual matrix data itself. If we were to use the print function instead to output our matrix A, we would get a very different looking output. In this case, we see the square bracket notation not only in the left margin as we discussed in previous sections, but we also get the square bracket notation along the top margin as well. These brackets actually contain the row and column indices, and we can see from this that if we wanted to specify a particular entry, we would write the row index followed by a comma and then the column index. Now, since these brackets refer to rows and columns, they don't actually specify particular entries. So they omit the row or column information when it refers to multiple indices. Right? So the first row is 1 comma nothing, meaning that it refers to all the entries in that row. We can also output our matrices using the cat function. However, in this case, we simply get the data from the matrix without any special formatting. The cat function really sees the vector of data and doesn't do anything special with the attached dimension attribute. So for the matrix A we've been using, we actually manually created it by first constructing a vector and then attaching the dimension attribute to it. R also provides a matrix function in which we can do this all in a single step. Now, this function gives us the exact same matrix we had in our previous example, but if we wanted to create a matrix, say, in row order rather than column order, we could use the by row argument of this function and set it to true to do exactly that. And now we see here in the output that 1 and 2 are no longer in the first column, but instead contained in the first row, because the data from the sequence 1 to 6 is being applied now in row order as opposed to column order. The matrix function will also use recycling when constructing matrices from vectors. If we attempt to create a matrix, again with 2 rows and 3 columns, but we only give it an input vector of, say, length 3, the matrix function will recycle that vector, fractionally if necessary, to fill the matrix entirely. So in this example, the vector 1, 2, 1 was repeated in order to create the 6 elements required for the 2, 3 matrix. In the event that we give more values than are required for a given matrix dimension, then R will issue a warning to let you know that only a subset of those values were actually used to create the matrix. And now I want to switch gears and talk about how you access the elements of the matrices, or how you index those matrices. So let's first create a matrix to play with. We'll call that B. And to access the element in the first row and say second column, we'll use the square bracket notation and we'll pass multiple indices, one for the row and another for the column. And we can actually use the single or double bracket notation here to achieve the same result. If we omit one of the indices, say the first one in this example, then we will access the entire column. Or if we omit the second index, we'll access the entire row instead. However, you may not use double bracket notation when attempting to access an entire row or column, as this results in an error. If we omit the comma, the indexing will occur just as if the matrix were a vector. However, the matrix data will be indexed in column order. Similar to vectors, we can use the names function to add names or labels to the elements of the matrix. However, when doing so, these names are applied in column order to the matrix data, and you see in the output that they don't actually appear here. To view these names, we actually need to use the names function. However, we still can use them to access the vector data within the matrix using the square bracket notation, just as we did for vectors. Also, just like vectors, when using the single bracket notation, we'll actually get the element with its name if it has one, and when using the double bracket notation like so, we get just the value back without the name. In addition to naming the individual elements, we can also provide both row and column names using the row names and call names functions. To do this, we simply call row names, pass it our matrix B, and then we assign it a vector of strings containing the row names that we want. And similarly, we can do the same with call names. And so now when we output B, we see that both the row names and column names are included in the output. And now, of course, we can use these names in place of numeric indices to access individual elements of the matrix. And just as before, if we omit one of these indices, we can retrieve an entire row or column. However, when doing so, it's important to notice that the output here is a vector. And this is because the dimensions of the output had a value of 1. And by default, the matrix will drop those dimensions. To prevent this, we can actually pass a drop argument with the value of false with the indices, like so. And now, instead of getting a length 3 vector, we actually get back a 1 by 3 matrix. So one last thing that I wanted to quickly show you regarding indexing of matrices is the use of negative indices, which remove the corresponding rows and or columns. If we pass as indices -1 for the row and -2 for the column, the first row and the second column will be omitted, leaving us with the values 4 and 6 from columns 1 and columns 3. Again, notice that this is a vector output, not a matrix. And this is because we didn't use the drop argument with the value false. Now moving on to concatenation. Since matrices are effectively vectors under the hood, you can manually use the same methods we discussed for vectors. However, R does provide two helpful functions, cbind and rbind, which will concatenate by adding rows or by adding columns. So let's start with the matrix C, created just like the previous examples, and let's use cbind to concatenate C to itself. In this case, cbind is taking two matrices, each 2 by 3, and concatenating them to produce a single 2 by 6 matrix as output. Similarly, we can use rbind to concatenate in the other direction. So if I write rbind C, comma C, you see here that we now get a 4 by 3 matrix, as it effectively stacked the matrices on top of one another.